So far in this module, we have been exploring a question that maximizes the consumer's utility by choosing the quantities to consume while being constrained by a fixed budget. We discussed how to find the optimal quantities Q1 star and Q2 star for each good to reach the highest level of utility. And once we found these quantities, we can plug them back into the utility function and check what is the level of utility we're able to attain given these exogenous variables P1, P2, and Y. And the result is described by the indirect utility function, V. Once the decision environment is fixed by the given set of prices and budget level P1, P2, and Y, then the indirect utility function is going to tell us a particular value instead of a function about the altitude on the utility hill we're able to reach, given this particular decision environment described by P1, P2, and Y. For instance, given that the prices are $2 and $1 for each good, and with a budget of $15, we're able to find a utility level of 12 units. Graphically, this will correspond to the height of the indifference curve we're able to reach at the optimal consumption bundle. The point is that once the exogenous variables are fixed, the utility level we can reach is just a constant. And let's denote this particular level by a notation of U bar. We've used this notation previously when we described the marginal rate of substitution. And let's use it again here, where the bar on top of U, just to remind us that this is a particular value as opposed to a function. Although in many real-life scenarios that involves consumption choices, we may set a fixed budget and then choose the quantities of goods that best suits our preferences. This is not always the case. For instance, if I plan a day trip with my family, it is more likely that I will have an idea about what the type of trip I would like for the day, and then I will choose the meal options and activity choices that minimize the cost of the trip, given that it would reach the standard of a good trip that I wanted for that day. In fact, in most scenarios when the budget isn't particularly tight, or the prices aren't particularly high, the utility maximization problem isn't necessarily the mental model that most consumers would use when it comes to their consumption choices. Instead, it is quite likely that consumers would operate through a mental model that minimizes the expenditure, given that the consumption choices will be able to deliver a certain level of enjoyment. To frame this mental model into a structure that we're already very familiar with, one might say that a more relevant model for consumers' choices should be choosing quantities to minimize expenditure, while under constraint that the consumption will be able to attain a certain amount of utility. In other words, if I have to attain a certain level of utility U bar while paying for fixed prices P1 and P2 for each good, then how should I choose these quantities Q1 and Q2 in order to minimize the expenditure? And when I make such choices, what is the minimum amount that I have to spend? Well, clearly, this problem is very similar to the utility maximization problem that we're already very familiar with, but it has some critical differences. It turns out that the answer to this question are exactly the same Q1 star and Q2 star as we have found in the utility maximization problem. And the minimum amount we have to spend is exactly the budget Y, which we started with in the utility maximization problem to reach this particular level of utility of U bar. This seems like a miraculous answer given how different these two problems are. If we try to write down this expenditure minimization problem, we're actually trying to minimize the cost that we're going to spend on each good combined by choosing quantities Q1 and Q2 and subject to a utility constraint that says the utility level that I'll be able to receive from these two quantities must be at least as high as this target level of U bar. Of course, choosing a quantity pair of 0 for Q1 and 0 for Q2 will minimize expenditure. However, it is very unlikely that such a choice would deliver the desired level of utility. In this constraint, notice that we're imposing an equality sign again, just like what we did in the budget constraint. Although our descriptive model only requires that the utility we obtain from Q1 and Q2 needs to be greater than this level of U bar or equal to U bar. Well, we put an equal sign here because intuitively, we won't choose any combinations for Q1 and Q2 that delivers more than what is required by the constraint, because in that case, we would able to further save on expenditures by dialing back a little bit in quantities to just satisfy the level of utility. If we compare this with the utility maximization problem we're very familiar with by now, you will notice that the utility function is no longer in the objective function, but instead it is in a constraint. On the other hand, the expenditure on the goods is now in the objective function of the cost minimization problem, although they're in the constraint of the utility maximization problem. And you will also notice that both this problem and the utility maximization problem use exactly the same two control variables of Q1 and Q2 to reach the objectives, either to maximize utility or minimize expenses. Because the utility maximization problem and the expenditure minimization problem are so closely related to each other, in formal terms of the optimization theory, the utility maximization problem is called the primal problem, where the expenditure minimization problem is called its dual problem. And now we will present these two problems graphically side by side to highlight their connections with each other. We have the utility maximization problem in this graph towards the left, where the choices of Q1 and Q2 are restricted by a straight budget constraint, which is fixed. And we're trying to reach the highest possible indifference curve on the utility hill. On the right-hand side, we have the expenditure minimization problem. We're similarly choosing the pair of Q1 and Q2. However, here we're restricted by a fixed indifference curve with a particularly given utility level that we have to reach. In this problem, we're looking for a consumption bundle that would incur the minimum amount of expenditures while reaching this fixed indifference curve. These straight lines work very similarly to the budget constraint on the left-hand side graph. And each one of them represents a different level of expenditure. The higher the curve is towards the upper right corner, the higher the expenditure it incurs. Let's think about these curves in more detail before we think about how to minimize the expenditure. All right, let's say that we end up spending a small amount of expenditure. Let's say C low here. Then if we spend all this amount of expenditure on good 1, we will get at most C low divided by P1 units of good 1, and we'll get at most C low divided by P2 units of good 2 if we spend all of it on good 2, or any combination in between of these two intercepts. Because just like the budget constraint, this line is precisely described by P1 times Q1 plus P2 times Q2 is equal to C low, which is a combination of Q1, Q2, whose expenditure is exactly C low. And the slope of this curve is exactly the same as the marginal rate of transformation for budget constraint, and that is just minus P1 over P2. Now, if we incur a higher expenditure, let's say C, what is the horizontal intercept for this curve? And what is the vertical intercept? What are the possible combinations of Q1 and Q2 that cost exactly C? Well, it's this curve between the horizontal intercept of C over P1 and the vertical intercept of C over P2. And all the combinations of Q1 and Q2 that incurs expenditure of C is exactly represented by this curve connecting these two intercepts. And what's the slope of this curve? It's exactly the same, which is minus P1 over P2 again. What if we spend even more? Let's say at level C high, like this. Well, again, the slope of the curve that describes the quantity that combines still remains the same at minus P1 over P2 because the intercepts are just going to be C high over P1 and C high over P2. Once the prices of the goods are given, the price ratio of the goods is fixed by the exogenous variables at minus P1 over P2. The curve of combinations that incurs the same amount of expenditure will all have the same slope. The same intuition about the budget constraint applies here as well. Regardless of how much money we end up spending, the trade-off between the two goods at any given expenditure level is always measured by the price ratio, just like the marginal rate of transformation, because if we only going to spend the same amount of money as we buy more units of good 1, we'll have to free up that amount of expenditure from good 2. And the amount we have to free up is exactly determined by the price ratio. Now we have established this view that all the bundles of Q1 and Q2 that can be seen as layers of parallel straight lines, where each line now represents a fixed level of expenditure, and lower lines represents lower expenditures, because you will only be able to get to lower intercepts on the graph. Now, with the help of these lines, we're ready to visually identify the solution to the expenditure minimization problem. Graphically, the expenditure minimization problem amounts to a very simple problem, where we're trying to search for the consumption bundle that reaches the lowest possible expenditure curve, while still touch this indifference curve that we need to reach. On this graph, spending C high will definitely reach this indifference curve, but we can certainly do better than that. It is definitely not the minimum level of expenditure to accomplish that level of utility. On the other hand, spending a lower level of expenditure C low will incur less expenses, but regardless of the combinations of Q1 and Q2 we choose, spending just C low is just not being able to reach this level of desired utility of U bar. The sweet spot lies in the expenditure level of C here, which corresponds to a particular expenditure curve that is just tangent to the desired indifference curve. This tangent point here represents the consumption bundle that incurs the lowest possible expenditure that reaches the utility level of U bar. The tangent point here represents the consumption bundle that incurs the lowest possible expenditure that reaches the desired utility level of U bar. These coordinates at this red point are our optimal consumption bundles for the problem. And the expenditure it incurs is the minimum level of expenditure needed to reach U bar when the consumer faces prices P1 and P2. Now let's compare the graphical representations of these two problems side by side. If you squint really, really hard, you will notice that these two red points are at exactly the same coordinates. You will also notice that the budget constraint on the left-hand side is exactly this cost-minimizing expenditure curve at expenditure level of C on the right-hand side. Moreover, you will find that this garnet colored indifference curve on the left and the one on the right are at precisely the same location. In other words, they represent exactly the same amount of utility. This is not a coincidence, and let me explain why. In the utility maximization problem, we start with a price ratio of minus P1 over P2, and we're locked down by a fixed budget of Y that pins down the vertical intercept and the horizontal intercept of this budget constraint. Now, with this budget fixed, it pins down the specific location of the expenditure, because as we maximize the utility by reaching up to the highest possible indifference curve, we're bound to spend all the budget of Y. So the budget of Y is eventually the expenditure we ended up spending on the utility maximizing consumption bundle, which, by the way, satisfies the tangent condition. Given this particular consumption bundle, we found the level of utility it delivers, which we denoted by U bar. And then, on the right-hand side, we're asking the opposite question. If we have to get this level of utility of U bar, and we have to pay the prices of P1 and P2, then what is the minimum level of expenditure that will allow us to do that? Well, it better be our budget Y, because when Y is all we have to spend, U bar level of utility is the best we can get. With any more expenditure than Y, we should be able to reach a higher level of utility than U bar. And with any less expenditure than Y, we wouldn't be able to get to U bar at all. So intuitively, Y should be the minimum expenditure level that's needed to reach this utility level of U bar. Once we see the problem this way, it is not surprising that it will be the same consumption choices in both problems that leads to the optimal choices. Technically, the optimal solutions must satisfy the same tangent condition, that marginal rate of substitution on the indifference curves are equal to the marginal rate of transformation, which is determined by the price ratios, which is also constant across both problems. Because the slope of the budget constraint and the expenditure curves are all determined by the price ratio. Moreover, the solution eventually lands on the same indifference curve with the utility level of U bar. So they must be identical. This pair of graphs is showing us that it doesn't matter if we start with a fixed budget level and try to reach the highest level of indifference curve, or if we start with that particular level of indifference curve and try to minimize the expenditure, we would land on exactly the same choice. The point I would like to highlight again is that the ultimate result of the utility maximization problem, which is this attained utility level of U bar, is the desired utility level that we started with on the right-hand side to minimize expenditure. On the other hand, the result of the expenditure minimization problem, the lowest possible expenditure is precisely the budget that pins down the constraint in the utility maximization problem. In short, one problem's objective is the other problem's constraint, and one problem's result is the other problem's starting point. And they both lead to the same consumption bundles of Q1, Q2 at the same coordinates. In general, not any expenditure minimization problem leads to the same optimal consumption bundle as the utility maximization problem. If we start from this pink indifference curve to minimize expenditure, clearly the optimal consumption bundle will land somewhere around here, as opposed to back at this red point here. The key that produces identical consumption bundles in both problems is that we started from the outcome obtained by this problem and then minimize expenditure on the the right-hand side. One major takeaway from this video is that the dualities between these two problems showed us how the utility maximization problem is a very relevant model of consumer choices, even though the consumer's mental model of consumption is one that is closer to expenditure minimization model. Both these models play very important parts in economics modeling, and they each have their own advantages in different applications. We'll see both of them reappear in many different places.